General relativity, step by step. We've been considering the linearized Einstein field equations, and we've come up with a solution to the linearized field equations that is basically a gravitational wave. And what I've been working on is to simplify the solutions so we can start to think about the physics. And I haven't quite finished yet. It's already very much simpler. You'll remember that in the previous screencast we had various manipulations that set this these elements here to 0. So we've just got these 4 to consider, and it's symmetric. So these two terms match. So we've only got 3 terms. But there's another simplification. You'll remember that in the theta gauge, or the theta gauge transformation, which we used basically to specify a large number of these things equal to 0. Where have I got it? Is it here? Yes, it is. This is my gauge transformation, and what we'll do is I'll ask what the trace of this matrix is here. So I'm going to copy that matrix, this transformation here. You'll remember that the theta transformation takes the matrix, or takes A from what it was before, and it subtracts these other terms that depend upon B, which was part of my my gauge transformation. All right, so let me just come down here and we'll start to think about this. Pinch in a little bit. Okay, so what did we have? We had x alpha going to gauge transformation theta, what it was before, and we subtracted a matrix, a 4 vector alpha times the cosine of k alpha x alpha, and we were choosing B in a sensible way to make various components vanish. And what effect did this have on A? Well, A mu nu went to gauge transformation theta, what it was before, minus 3 separate terms. K mu B nu minus K nu B mu plus flat space metric eta mu nu K pi I was using for the summation variable B pi. So in this gauge here, I ask what is A mu mu equals the trace of A. Well, let's just go. Let's just do it. Let's just ask. Well, let me rephrase what I'm trying to do. I'm trying to lower one of these matrices, one of these indices, and sum them. So I'm really asking for eta. We've got 2 upstairs indices, mu nu, A mu nu. That's the trace of A. That's A mu mu, I guess, equals that. Well, that goes to, well, it's just this equation here, but multiplied on the left by mu nu times, I'll just write it out, A mu nu minus eta mu nu, K mu, that's that term there, B nu minus eta mu nu again, K, it's mu and nu, here it's nu and mu, they swap over, nu B mu, plus, now it gets a bit more interesting, eta mu nu K pi B pi. Okay, equals. This term here is just the trace of A. It's just the trace of A before the transformation. So the trace of A, no, let me write it out more accurately. It's the trace of A goes to, under a gauge transformation of theta, what it was before, minus some other stuff. Now, these 2 terms here, I'm going to do it in a different colour, if my OneNote will let me do it. It probably won't. Here we go. I'll do it in blue. Is that blue? Yeah, we're in blue. I'll pinch in a little bit. These 2 terms here, this term here and this term here, are actually the same. Because we're summing over mu and nu, and they're just dummy indices, so I can swap them over if I want. Okay, let me go back to black. If I I can. Black. Boink. Is that black? Yeah, that's black. So it's minus 2 eta mu nu k mu b nu plus, now what's this thing here? It's always good to write out the minus 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So that's plus 2, because it's 1 2 3 minus 1 is 2, k pi b pi. Well, that's nice. Right, I had to pause it there for a few minutes while I collected my thoughts. Normally I can blame the computer for cocking up, but here it's me. Let me show you the problem I had. I had this equation here. It took me some considerable time to sort this out. It looks like that equals the trace of A, because these two terms are equal and opposite. You see how this term here, I can rewrite this term here to be minus 2k. You see we've lowered one index. I can call it what I like. I'll call it an alpha, b alpha, plus this term here, which is 2k pi b pi, equals the trace of A. So it looks like this gauge transformation of theta doesn't change the trace of A, and I wanted to constrain the trace of A to be 0. But I made a mistake, and I'll show you what it was. And this is, after all, general relativity with the mistakes left in. I'll get rid of all of that. Delete. It's not plus 2. It's plus 4. It's because eta mu nu equals 4, not 2. I was thinking it was 1 2 3 minus 1 is 2. But it isn't, because minus 1 times minus 1 equals plus 1. So we've got this. There's lots of things like this that you just kind of know after a while, but it's easy to forget stuff. So let me just rewrite my little equation here as the trace of A is mapped to, under my gauge transformation of theta, what it was before, plus 2k pi b pi. Now, if I go back to this line of reasoning here, you'll remember that the first line of restriction, or the first restriction imposed by the Lorentz gauge condition, didn't really kick in. It didn't really kick in at all, which is a bit disappointing. So what that means is we've got an extra degree of freedom to use in our gauge transformation that allows me to modify the trace of A. So what I want to do is to use it to make the trace of A equal to 0. All right, and that's quite nice. So what I'm going to do is I'm going to go back to, if my interface behaves, which it isn't, I'm going to go back to my original little picture. I'm going to observe that I can force the trace, which is that plus this plus this plus this. Actually, it's minus 1 times that, but it doesn't matter because it's a 0. So alpha plus gamma plus 0 equals 0. So that tells me that alpha equals minus gamma. So I can rewrite that to being a minus alpha. Right. Let me copy that equation down here where I can talk about it. We'll talk about what it means. We've got our nice matrix here, or written in matrix form. It's not a matrix. That's T, X, Y, and Z. T, X, Y, and Z. We showed that it was transverse. All these are zeros. We picked a special value of K, which was minus omega 0, 0 omega, so the wave was propagating in the z direction. That made these guys equal to 0. We then observed that we had a extra degree of freedom that I could use to constrain that. I'll not call it x, I'll call it an alpha. We could constrain the leading diagonal to sum to 0, which was that one, and we know it's symmetrical, so whatever that is, we've got that there as the same value. So now we have 2 degrees of freedom. of freedom equals 10 minus 4 for the first. No, we haven't. We've got 6. We've got 10. Just a minute. My interface is not behaving. Sorry, let me rephrase that. We've got 16 degrees of freedom because we've got a 4 by 4 tensor. We've got a second rank tensor. It goes down to 10 because of symmetry, which went down to 6 because we had a gauge freedom which I called psi, and then that went down because B had 4 elements down to 2. And here are the 2 elements, alpha and minus alpha for these 2 terms here, and beta here and here because it's symmetric. Oh, absolutely fantastic. So let me rephrase it all together. We've got H bar, transverse traceless gauge, which allows me to simplify it down to this nice form here. Mu nu equals A mu nu, which is this matrix here, which is nice and simple. It's only got 2 degrees of freedom, times e to the I k alpha x alpha. And there is my gravitational wave in its most simple form, propagating in the z direction with wave vector alpha. And A mu nu is this rather beautiful, very simple, only got 2 degrees of freedom. We'll see that the 2 degrees of freedom correspond to the different polarizations. But for the moment, I just want to marvel in that beautiful equation there. I'm going to stop there. Stop. Just look at it. Just look at it. Isn't that wonderful? Isn't that wonderful? We've got a steady component here and an oscillatory component here, and it's in the simplest possible form. Wouldn't it be nice if we could detect these? Yeah. Yeah, that would be nice, wouldn't it? Stop.